All right, everyone. Welcome to the seminar today, and it's my pleasure to introduce Tim Hermans. He comes from the Netherlands and is visiting New York for a few days. He's currently a postdoc at the University of Utrecht, and he did his PhD at the NIOZ Royal Netherlands Institute for Sea Research. Tim is an expert on sea level change and extreme weather events, particularly flooding. He's also a chapter scientist on the most recent IPCC assessment report, Chapter 9. And today he's going to talk about extreme storm surges and how to work on that with machine learning. So I hope there's a lot of overlap with folks over here. Thanks.
Perfect. Thank you. Can you hear me? Is the microphone working? Okay, perfect. Well, thanks a lot for having me here today. By the way, if you have any questions for clarifications in between, please just feel free to ask them and interrupt me. So yeah, my name is Tim. I will talk today about computing extreme storm surges using machine learning, neural networks specifically. And Julius already said it, but I'm from the other side of the North Atlantic, Utrecht in the Netherlands. It's a very nice city. If you ever visit the Netherlands, please go there. I did a PhD on sea level change, specifically on regional ocean models, which I used to refine the simulations of global climate models. Should I? Yeah. No problem. Yeah, that's better, I think. And then I also did some work on global mean sea level projections and sea level variability. And by working on those topics, I kind of was involved in the IPCC report in 2021, where I contributed to sea level projections and also projections of extreme sea levels. So that has a nice link to today's presentation. I'm currently working on extreme sea levels, doing extreme value analysis. I did a study with Julius on compound flooding. That's basically how we met. And maybe some of you were attending a presentation that we gave together a while ago as well. And so today I will give a bit more context on those extreme sea levels, talk about why I want to use data-driven models, and show you some of the results that I've got so far. So first, for some context, and this is not yet machine learning related, but we will get there. So there are two different types of changes in extreme sea levels. And what's often being projected are changes in extreme sea levels that we call static. So basically, you could have a distribution of extreme sea levels looking like this. So depending on their return frequency, they could be lower or higher. And we can then assume that this distribution is going to change, is going to stay the same in the future, which is not entirely true, but we can assume that. And then add projected sea level rise for a certain year, for instance, 2100. So by doing that, the whole baseline of those extreme sea levels will be raised. And then you can do some calculations like the following. So for instance, you could wonder how much more often is the extreme sea level with a return frequency of once per century historically going to occur in the future, for instance, annually. And that would result in what we call an amplification factor, in this case of 100. And as I will show in a bit, this is a typical computation that IPCC reports in the past decade or so have been reporting. Because it's relevant for the machine learning work, I'm going to go a bit more into detail on this method. So how do you come up with a distribution of extreme sea levels? Basically, you take an observational record of those sea levels and you define a certain threshold above which you define sea levels to be extreme. For instance, the 99th percentile of observations is often used. So you would end up with a series of extreme sea levels with a certain height and a certain frequency of occurrence in the observational period. And then to say something about events that you have not yet observed with an even lower return frequency, you can fit an extreme value distribution. And basically that results in a curve, which we call a return curve, linking the return height to the return frequency. Now, in those static projections that I just explained, we would add a certain sea level rise projected for an arbitrary year, raise that return curve up, and then see where the historical centennial event, so the event with a return frequency once per century, will end up in the future and come up with a certain amplification factor. So that's what this looks like in practice. As I said, this is what the IPCC did. So for instance, this led to some headlines in the summary for policymakers that extreme sea level events that occurred once per century in the recent past are projected to occur at least annually at more than half of tide gauge locations in 2100. So that feels quite significant. However, at the same time, it also doesn't really say a lot, because how relevant is the historical centennial event for a certain location? Maybe there's also flood protection in place. So as a small sidestep to this presentation, I wanted to show some work that we did in the recent past, where we replaced this historical centennial event with flood protection standards that are estimated in different places. So for instance, in the Netherlands, there are dikes that are designed to withstand events that occur once every 10,000 years. So these are very high standards, which are also difficult to estimate. But in other locations, there may be relevant standards, for instance, once per decade or maybe even annually. So by replacing that reference frequency with a more meaningful frequency, you can make calculations like these, where we're computing when current flood protection standards will be exceeded 10 times as often. For instance, a relatively high emission scenario, and then you can make some conclusions, for instance, that this will happen within the coming 30 years at about a quarter of tide gauge locations. Okay, so this is some background. Let's get a bit more into the machine learning aspect, because there may also be changes in the distribution of those extreme sea levels, even though people often assume that they are not important. So there may be changes due to changes in tides, waves, and what I'm interested in specifically is changes in storm surges. Here you see projections that exist at the moment for changes in storm surges, apart from changes due to sea level rise itself. This is a map of changes in the storm surge height with a return frequency of once per decade. And this is based on a relatively small ensemble of climate model simulations. But even still, they show some patterns of change. For instance, increases in the storm surge level here and there, decreases over there. But more important for this talk is that the models don't really agree a lot about whether these changes are positive or negative. So this is not the most clear plot ever, but the darker the colors here, the more models agree about the sign of the changes projected. And as you can see from the light colors at many places, there isn't that much agreement between climate models, meaning these projections are quite uncertain, both due to differences in climate models, but also due to internal variability, which is in this specific case especially important because we're looking at a period that's quite close to the period where we are in now. So there's uncertainty because of those small ensembles of climate model simulations that are being used for projections like these. And why are those ensembles so small? That's because global climate models don't output storm surges, or at least not reliably. They simulate changes in atmosphere, wind and sea level pressure, for instance, but you need an offline method to translate those atmospheric variables to changes in storm surges. And typically, a hydrodynamic model is used for that. Of course, that takes computational power. Therefore, ensembles have been limited in size so far. So this got me wondering, can we do this better, faster, more efficiently? For instance, by replacing the hydrodynamic model with a data-driven model like a neural network. If that works, it would allow us to base projections on much larger ensembles of climate model simulations and reduce those uncertainties that I just talked about. However, there are a few problems. In the literature that I've read, there are quite a few examples of machine learning to compute storm surges for specific events, for example, during tropical cyclones, using information about our path and other properties. However, there have been fewer applications looking at reproducing whole time series of storm surges based on gridded atmospheric data. And the studies that are there, they didn't really look into extreme storm surges, which are in the end what we are most interested in because these are the ones causing flooding. And they didn't really evaluate how well their models perform at simulating those extreme storm surges, neither did they train their models specifically to predict the extremes. And that's what I will talk about on the next slides. Second challenge is applying those models once trained to climate model simulations, which is difficult because the climate models have biases. And also they may simulate changes in the atmosphere that push their distributions beyond what is being observed at the moment. And that may cause the neural networks to have to extrapolate to compute storm surges, and they are not that good at it. Any questions so far? Okay, that's great. Okay, so let's make it a bit more concrete. The study site that I'm looking at is Northwestern Europe. We selected a few tide gauges, namely the ones indicated on a figure based on their available data and also on geographical distribution. And the data that we use are tide gauge measurements. And an example of that is shown for Den Helder, which is a city at the Dutch coast. And first of all, what we did through those observations is to remove the tides, because that's not what we're interested in predicting. So we are left with something that's hopefully a non-tidal residual and mainly caused by storms. And then, as is common for model training, we split it up the data into three different parts. A part to train the models, a part to validate the models and see which hyperparameters are most important and work best, and a third split of the data to evaluate how well the models generalize once trained. And the data that we use to predict those non-tidal residuals, which I will refer to as storm surges from now on, is atmospheric data from the ERA 5 reanalysis. So it's based on observations, not only at the place where the tide gauge is, but also in a box of 5 by 5 degrees around it. And also not only at the time step at which we want to predict the surge, but also at multiple different time steps before. So this data is available at a hourly frequency, but because eventually we want to apply it to climate models, we downsample basically the data to a 3-hourly frequency. Because climate models, the data of the climate models is often only provided at 6 or at best 3-hourly frequency. So we want to be as close to that situation in training the models as possible. And in evaluating, as you will see in the next slides, I'm focusing on exceedances of the 99th percentile, because this is what is typically used for those extreme sea level analyses that I just showed. Okay, so that automatically also raises a problem, because those exceedances, the extreme storm surges, do not happen that often. They are underrepresented in the observations. So by minimizing a certain loss function, for instance, the mean square error, the model will be biased towards the more moderate events. So we wanted to test something to kind of counteract that. And we did that by introducing a weighting factor, which is based on previous work applied on a different setting. So that weighting factor basically puts more weight on observations that are more rare. So as you can see here in this figure, these are the observations on the x-axis, standardized, and this will be the weight that is given to them. And depending on this hyperparameter alpha, the weights placed on the more rare events are higher or lower. So for an alpha value of 0, we don't do any density-based weighting. So all the observations have a weight of 1. And the higher the alpha, the more severe we weight the extreme events more. And we tested until an alpha value of 5. This will come back in the results as well, so it's important to remember. Then we tested two types of neural networks, and I guess that many of you will be familiar with these. First of all, we used a model with an LSTM layer, long short-term memory, that looks at temporal features in the data. But we also wanted to test what the added value is of also looking at spatial temporal patterns using a convolutional version of the LSTM model. So before I show the results, let's here list the questions that we wanted to answer. First of all, what is the effect of introducing these density-based weights for predicting extreme storm surges? Secondly, is there any added value of introducing convolutional layers that look at spatial temporal patterns? And thirdly, how well do the neural networks, once trained, actually perform? So we have two different benchmarks for that. First of all, a very simple multilinear regression model. And secondly, a very complex hydrodynamic model with a very high resolution, which is called the Global Tide and Surge Model, GTSM. So basically, those two are used to provide some context to the performance of the neural networks. Okay, and then we trained those models multiple times using different hyperparameters and also using the same hyperparameters to see the effect of the randomness in model training. But that's not really what I wanted to talk about. So let's look at the results. First of all, how important is it to introduce those density-based weights? This is a quite complex plot, I realize, but I will break it down for you. So what we see here on the x-axis is the root mean square error evaluated only at places where the observation exceeds the 99th percentile. So basically, it's the root mean square error, RMSE, of extreme observations. Then we have multiple locations, those 9 selected locations that I mentioned here on the x-axis. And we also have multiple colored circles. Every circle for every location is a single LSTM model that was trained with different hyperparameters. And depending on their color, they have a different alpha hyperparameter, so a different degree of density-based weighting, either no density-based weighting or density-based weighting with a different degree. So, oh yeah, and then a final thing, those black bars, they indicate the relative root mean square error. So this was the absolute root mean square errors in meter, but the 99th percentile, so the extreme sea level at each location also varies, depending on the nature of the location. So for instance, for the Danish coast, Esbjerg, the 99th percentile is fairly high. For other locations, the 99th percentile is quite low. So by comparing the root mean square error absolute to those color bars, you can get a sense for the relative error at every location. Okay, so what is the effect of those hyperparameters here? Basically, we see that the higher the alpha value, so the more we weight extra for extreme events, the lower the root mean square error becomes, which is, I guess, somehow expected because we punish the model more for being wrong at the extremes. For most locations, the relative error is between 20 and 30% when we use an alpha value of 5. There's one location at the UK coast where we're not so happy with yet, and where the relative error is quite large. So this indicates that the density-based weighting for the LSTMs is important to reduce the root mean square error, but this is only for observations that are extreme. It's also relevant that the model predicts the extremes at the right times. So for that, we introduced another metric, which is the F1 score. That depends on whether the predictions predict extremes at the right time steps or not. So basically on false negatives, true positives, false positives, and gives an harmonic mean of those scores. So it doesn't really matter if you don't completely follow this, but just remember that the higher the F1 score, the better the neural networks are at predicting the extremes at the right time. So I have a similar plot as before, but now for the F1 score. And there you also see quite some variation in the score per location. But the behavior, depending on the density-based weighting, is a bit different than for the root mean square error, which is interesting. So by introducing density-based weighting, so going from 0 to 1, usually for most locations, the F1 score slightly improves. But then if you turn up the density-based weighting even more, you see that the performance in some cases also starts to drop. So that is caused by the model catching more true positives, so predicting more extremes, but also predicting more extremes at times when it shouldn't. So the number of false positives also increases and the model becomes less precise. So yeah, and there are 3 locations where the F1 score isn't that great in general. So that means that by introducing density-based weighting, we can increase the performance, but the alpha value that you need to use depends on the location and also on the metric that you want to optimize. So it needs to be tuned. And while it increases the performance at predicting extremes, it worsens the performance at predicting the moderate events, which I guess is expected. But I'm saying that here anyway, because it's important to realize that it's a trade-off between predicting extremes or predicting moderate events, and it's hard to do both at the same time very well. Is this clear so far? Yeah, perfect. Okay. Yeah, I also said that I was going to compare the LSTM models to other neural network architectures and other models. So let's make this plot a bit less complicated by taking the best performing models, which I selected based on their joint performance at both metrics. So that cleans up the plot nicely. And then I will also now show you the performance of the convolutional LSTM models, which are depicted by the red squares here. I only tested this model for a hyperparameter of alpha of 5, so the most high density-based weighting. But still, you can see that the convolutional neural network in general performs better than the LSTM models. Namely, the red squares here are often below the red circles. And the same goes for the F1 score. So apparently by using a convolutional layer and by trying to capture those spatial temporal patterns, you can get the models to perform better, which is what I state here. And now we still don't really know how good this is. So it would be interesting to compare it to the hydrodynamic model as well. So here you see the performance of the linear regression model. That's the white diamonds in the color bars. And we also have the hydrodynamic model, abbreviated as GTSM, which are the white diamonds. And then when you look at this plot, you can see that the white triangles are often performing as good as the worst performing neural network, or even worse. That goes for both the root mean square error and for the F1 score, so the timing of predicting the extremes. While the hydrodynamic model is often at the upper end of the performance, so has a lower error or a higher F1 score. So the neural networks are somewhere in between. However, if you look at the convolutional neural networks, you see that in some cases, at some locations, the performance actually gets pretty close to the hydrodynamic model, which is encouraging, especially because we trained the neural networks with 3 hourly frequency, but those hydrodynamic model simulations were forced with an hourly atmospheric frequency. So in that sense, the hydrodynamic model already has a bit of an advantage. So the fact that we are getting that close is quite encouraging. So basically, based on this plot, we conclude that things look okay at 7 locations in terms of the relative performance of the neural networks to the hydrodynamic model. However, this was just based on a validation split that we used to evaluate different hyperparameters. If we start looking at how well the the models generalized to the test split, so the data that was withheld from training and evaluation until this point, we see some interesting features as well. So this figure shows the root mean square error relative in the validation split against the test split. And the different colors are different locations. So what you can see from this figure is that the generalization is pretty okay for most locations, but this location really stands out as a location in the Mediterranean Sea. And we don't know yet exactly what causes this behavior, but it may be that in the Mediterranean Sea, the storm surges are not that large to begin with. So there are other factors, for instance, due to precipitation, river discharge, maybe also density-driven baroclinic changes in the ocean that may cause sea level to be extreme as well. And maybe those events are not evenly distributed over the different splits, which aren't that long to begin with. If we look at the generalization in terms of the F1 score, we also see this to some extent. So here, the performances are a bit more scattered, but generally fall also onto this 1-1 line. Okay, so that means that we are left with 6 locations, because at the location in the Mediterranean Sea, Alicante in Spain, the generalization is not that good. So in the next slide, I will zoom in a bit on the predictions in the test split for the remaining 6 locations, considering only the LSTM and the convolutional LSTM model with the highest density-based weighting. So that's what you see here. These are scatter plots of observed storm surges higher than the 99th percentile versus the predicted storm surges either by the neural networks or by the hydrodynamic model. So that's in gray. The orange one is the convolutional neural network, and the other one, the one with the LSTM layer. This diagonal line here is the 1-1 line, so the closer the circles are to that, the better the model performs. So we use this plot to kind of dig into the behavior of the predictions really at the upper end of the tail of the storm surges. So on the right of this vertical line are observations that exceed the 99.9th percentile. So far we were evaluating exceedances of the 99th percentile. So what happens for even higher extremes? What you can see is that often the hydrodynamic model is overestimating the observed extremes exceeding the 99.9 percentile, whereas the neural networks, especially the LSTM model, is almost always underestimating it. This is kind of alleviated by using a convolutional neural network, but still the underestimation is quite visible. This also has an influence on the root mean square error. So we used, in the previous figures, I used the 99th percentile to evaluate the root mean square error. And then you saw that the convolutional model had a comparable error to GTSM, the hydrodynamic model. But if you use the 99.9 percentile, which makes things very sensitive, that's of course true. But then you see that the neural networks compare worse compared to the hydrodynamic model. So apparently, the further you go into the upper tails of the distribution, the more the neural networks start to drop off, possibly because there are just not that many of such high extremes in the training data. Yeah, and this figure kind of confirms what I just said. So these are box plots of the error distributions for the different neural networks and hydrodynamic models. This is the relative error for the 99th percentile and for exceedances of the 99.9 percentile. And then you see really for those really the most high exceedances, the neural networks often underestimate the observations, whereas the hydrodynamic model can also overestimate them. Okay, so first of all, to answer the research questions and summarize it a bit for you, the effect of introducing density-based weighting is positive in terms of both the root mean square error and the timing of predicting the extremes. However, the alpha value, the hyperparameter that controls the extent to which we extra weight those extremes, needs to be tuned depending on location. We see added value for exploiting the spatial temporal features in the data by using a convolutional LSTM layer instead of an LSTM layer. And this is an interesting result because previous studies have claimed that a convolutional LSTM layer doesn't really improve things. However, they used atmospheric data in only 1.5 by 1.5 degree box around each tide gauge. And perhaps that means that to really exploit the spatial temporal features, you need data over a larger region. Finally, how well do the neural networks compare to the other models? It was clear that they outperformed the multilinear regression model, which was also used in previous studies. So that's good to know. Especially the convolutional LSTM models approximate the performance of the hydrodynamic models, which is encouraging for application to climate model simulations, which I will talk a bit more about in the next slides. However, we still see an underestimation of those highest extremes. And in the discussion after this, I would be happy to take any suggestions for how to resolve that. So based on this, we have several ideas for follow-up work, next steps. First of all, try to see if we could use other predictors besides just wind speed and sea level pressure. So as I mentioned, this location in the Mediterranean Sea, there are all other processes that might be relatively important, for instance, related to precipitation and temperature. Perhaps we could improve the performance of the neural networks by including those. Some studies have shown that waves as a predictor are important, but this introduces another limitation because waves are not available from global climate model simulations. So that would kind of bypass the purpose. Of course, there's probably a lot of room for trying different architectures. Again, if you have ideas, then please let me know. We didn't do that much hyperparameter tuning, so I would expect this to improve the performance a bit more. And something that I've thought about also is to try to test strategies like synthetic minority oversampling in addition to the density-based weights that we introduced. However, I'm not entirely clear yet how best to do that, while also respecting the spatial temporal patterns in the input data. So any help with that would be nice. Okay, so given that the performance of especially the convolutional neural networks looks quite okay, will be interesting to explore trying to apply them to climate model simulations. So there's a model intercomparison project as part of CMIP6 called HiResMIP, which includes high resolution global climate models with simulations until 2050. So it would be quite nice to apply the neural networks to that, come up with changes in storm surges, and then there is also a benchmark data set to evaluate those changes. Namely, the same model that I referred to earlier was used also forced with those high-res-MIP climate model simulations to compute changes in storm surges. So by comparing the two against each other, we could learn a bit more about those obstacles that I talked about before and see how well the neural networks can be used in this context. However, I can't show you results yet because there are some issues here. One of them has to do with the fact that the temporal resolution of the high-res-MIP simulations varies. Some of them have a 3-hourly frequency, others have a 6-hourly frequency. And to use the 6-hourly frequency, I would have to retrain the models also on 6-hourly observational data. That would probably decrease the performance. Secondly, the study that produced those simulations with the hydrodynamic models also introduced sea level rise as a forcing. They did so by lowering the bathymetry of the models, increasing the water depth with the projected sea level rise. And that increased water depth has an effect on the storm surges that follow extreme pressures and wind. However, I don't really see a way yet to introduce this in training the neural networks because the sea level rise observed so far has not been as large as what is projected in the future. So one thing I would add to those recommendations is that we need climate model outputs at higher resolutions temporally. So these should be available because they have the models are run at a much higher temporal resolution than the one that the data are provided at. However, they're simply not available from the databases. Well, actually, you can do very interesting research with them. So that would be a recommendation from my side for future coupled model intercomparison projects. And with that, I'm done. I'm happy to answer any questions or hear suggestions. Thank you.
Great. Thank you, Tim. Does anyone have any questions in the room? And if you have questions online, please either use the raise hand function or pop a question into the chat. Anyone in the room?
Do you think this has sort of implications also more on a operational basis, on sort of like predicting extreme events sort of on a short horizon to sort of avoid that rather than sort of long-term risk projections?
Yeah, I think there are definitely parallels, and I have the feeling that people are way further with that than with the kind of things that we're trying to do at the moment. So perhaps there are lessons to be learned there. I'm not aware if they also use these schemes to weight extremes more, perhaps because it's also in their interest to forecast the more moderate events. So I don't really know how that works in that context, actually.
Any more questions in the room?
I have a question regarding how your data is relative to the IPCC mitigation. So assuming that you're following a mitigation curve, how does this data relate to those pathways? For example, in the beginning you said that every 100 years there would be this example of extreme storm surge, and then that translates to once every year. And then now what frame of reference is that related to in terms of mitigation according to the IPCC?
Right. Yeah, I guess that's to say something about that, you would first want to calculate the sea level rise under a mitigation emission scenario. That's possible. Of course, there's this kind of sea level legacy or committed sea level rise that has already been built up by emissions that have been by how do you say that? By what has been emitted before. So that would be one. You could calculate the difference in sea level rise between built-off scenarios or maybe SSP 3.70 or something. And more related to what I'm trying to do here is you could get atmospheric changes from global climate models run under overshoot scenarios or something like that, and try to apply the neural networks to that, see what changes in storm surges that would result to in comparison to the more regular emission scenarios that in which there is no mitigation, and then say something about the difference in the changes, if that makes sense.
And we do have a question online from Jiarong Wu. Can you speak a bit more about the GTSM in terms of what atmospheric inputs they take, and is it of similar spatial/temporal resolution to the neural network inputs?
Great question. Yeah, perhaps forgot to explain that. So the data that goes into GTSM, the hydrodynamic model, is exactly the same data as what we're using to train the neural networks with, in the sense that it's the same variables, so wind speed and sea level pressure from the same product, ERA 5. The spatial resolution is also the same, but the temporal resolution in their case was higher. Apparently, they didn't bother running with a 3-hourly frequency when there was also an hourly frequency available, which I understand. But in our case, it makes sense to do that if the goal is to eventually apply it to the global climate model simulations, which are only available at a coarser temporal resolution.
Thank you. Any more questions?
Thank you, Tim. Great presentation. So my question is about the F1 score. So as far as I know, F1 score is a special case of the F beta score that balances the precision and recall. And in your case, what is more important, the precision or the recall? Because so maximizing the recall means that you reduces the number of false negatives. Okay, so what is in your case and according to the application better? So thank you.
That's a good question that I'm actually also still a bit undecided on. So in a forecasting context, I think that this is a different choice because you want to predict the extremes and you want to have true positives more than you care about reducing the number of false positives. In this case, it's maybe a bit different because in the context of applying the extreme sea level analysis, you would then start with the predictions, calculate the 99 percentile of the predictions, and use the exceedances of that 99 percentile that are predicted. But those could be falsely extreme. So in that sense, it would be good to reduce the false negatives. But if that comes at the cost of simulating fewer true positives, that would also be bad for the extreme sea level analysis. So I don't know really. So it's not a direct reflection of what is important for the extreme sea level analysis, I think. Yeah.
Any more questions?
Nice talk. So I was wondering if you could comment a bit on maybe the nature of the invariant coastal configurations. I mean, that depends on the site. You know, you have some really bendy coasts. You have like islands and barriers and things, and presumably that would impact local relationships. And does that need to be taken into account?
Yeah. So that's an interesting idea. Thanks. Right now, we are training the models individually, difficult word, for every location. So I guess in some sense, the influence of the coastal setting is taken into account by doing it in that way. But I can imagine that the coastal configuration also changes over time because of sea level rise or erosion, maybe also because of channels that people make that affect the tides. So yeah, definitely. I mean, I think for the Dutch coast specifically, there hasn't been that much research into changes in tides, and it's also quite difficult to model because it requires taking into account very local features. I don't have concrete ideas for considering those features in the training of the neural networks, to be honest. But I think it would be definitely interesting to consider. Yeah.
Great. Any more questions? If not, another round of applause for Tim. Thank you.
Thank you.
And